You're listening to the Stephen Wolfram Podcast, an exploration of thoughts and ideas from the founder and CEO of Wolfram Research, creator of Wolfram Alpha and the Wolfram language. In this ongoing Q&A series, Stephen answers questions from his live stream audience about science and technology. This session was originally broadcast on December 11, 2020. Let's have a listen.
Okay, hi everyone. Back for another episode of Science and Technology Q&A for kids and others. And we have a variety of questions left over from last week, which I thought I would start with. So let's see, we have one from Parmenides here. Who are your favorite science fiction authors? What are your favorite stories and movies? You know, I am a terrible reader of fiction. It's one of those things where I keep on saying, later in life, I'll read fiction, but I never get around to it. I did read some science fiction when I was a kid, and I wasn't always so thrilled with it because I was always interested in, what are the key ideas about the world, the future, whatever, from the science fiction. It's like, let me take this 50-page story. I just want to compress it to the one page, which is, this is the idea about the future. And I wasn't at that time so interested in the kind of human story. I have to say that in more modern times, the whole question about how humans interact with technology in the future and so on, I find much more interesting. And I think there's a lot that can and should be explored in science fiction about the way that we think about the human condition, its relationship to kind of the digital analog of humans, our relationship to AI, these kinds of things. And I think there's a lot that can be explored where to write it as something written as sort of philosophy would be much harder to understand than writing it as something more like a story. But having said that, I can talk about a few things a few sort of science fiction kinds of things that I found interesting or whatever. I think the first, mostly movies rather than books. The first one that certainly had an effect on me was 2001: A Space Odyssey, which came out in 1968. And actually it happened to be the very first movie that I saw in an actual movie theater. But that's neither here nor there. But 2001 was interesting to me at the time for its very sort of bright vision of the future. And really, it was a mixture of a story about space and a story about computers. And I went back and looked at it back a couple of years ago now at its 50th anniversary to try and sort of analyze the movie and what was in it and what was significant about it. I mean, I think that in a sense, the human characters in the movie, which I kind of respond to much more now than I did when I was 8 years old or whatever, are kind of interesting for being uninteresting, so to speak. The AI, the computer, the HAL 9000 is in a sense one of the most human characters in the whole movie. But there were themes in that movie that I thought were interesting about kind of the sort of large span of time from sort of the earliest interest in sort of science by kind of the hominid, pre-human, ape-like creatures at the beginning of the movie, flowing through to kind of the future of the extraterrestrials and so on at the end of the movie. And I think also it was interesting to see, that was a place where I could kind of see at least a vision for what computer technology of the future might look like. It was interesting to look at it 50 years later and see what was gotten right, what was gotten wrong. I mean, there were a lot of very interesting mistakes. Like, for example, one of them is the idea of soft windows on the screen just wasn't there. So for them, different functionality was a different physical screen with doing different kinds of things. The idea of sort of everything as software wasn't really there. There were, there was a very talk to your computer type movie. Now, in a sense, some of the things that I've done in developing software technology have been things that have sort of filled out some of the things that were kind of anticipated in a movie like that, about sort of be able to ask your computer questions and have it give meaningful answers, things like this. But that was, I think it's also kind of charming in that movie. There's, you're talking to the computer. There's no notion of any kind of computational language that the computer is using or that anybody is using to sort of be precise. There's a certain amount of human precision language that sounds like, air traffic control lingo. That's kind of the taking natural language and making it more precise, just like a legal contract would make things more precise. But it didn't get to the point of understanding that there will be sort of a computational language that will be a bridge between the human and the computer. And there are just a few brief moments where screens flash up essentially computer code, which is sort of a charming mixture of mathematical notation and I think an early version of the PL1 computer language that IBM developed. IBM was sort of the main consultant for that movie in terms of computer technology. But so that's an example of a movie I thought was interesting. I think, oh gosh, in more recent times, there's lots of them. Hasn't happened so much during this pandemic, but usually I kind of make a point of, I don't watch any television, but I do try and see a movie every week or two as a way to sort of keep in touch with what's happening in the world in general. But other science fiction movies I might mention, another one I thought was interesting was the Contact. Maybe there's a theme here of extraterrestrial movies between 2001, which is ultimately an extraterrestrial first contact movie, and Contact, which is an extraterrestrial first contact movie. And movie I helped with a bit, Arrival, which is another extraterrestrial first contact movie. I suppose Contact, I thought was interesting movie. It portrays it was somewhat realistically portrayed version of kind of what it would be like for humans to get an intelligible signal from extraterrestrials, and what the kind of human response to that would be, and how one would kind of understand what it was, and a little bit of the human story behind sort of a discovery in science. I'm trying to think. There are so many other science fiction movies from the sometimes movies will have a particular idea in them, like Minority Report, which I'm not sure is a particularly wasn't particularly a movie that especially resonated with me in many ways, but its whole sort of gesture-based interface was something that became a very notable feature of that movie. It's always interesting when there's always a question of to what extent are there really sort of science, technology, etc. ideas in movies? To what extent are movies really human stories? And I think to a large extent, movies, to be successful, have to be human stories. If they're movies about, people like watching movies and find interesting movies which are ultimately about people, perhaps people portrayed in a setting where they're, traveling on a spacecraft to Jupiter or something, rather than being in just hanging out, in their suburban setting or whatever. But still, it's got to be a story about people. And in a sense, some of the stuff that I find most intellectually interesting is the places where sort of that intersects with technology and science and so on. So sometimes those pieces are very much kind of extracted from the main part of the movie. Let's see. I think if people want to ask about particular movies, I could probably give some more analysis, but it's at least a rough thing. So let's see. Someone is asking here. Crunchy is asking, why do people have emotions and feelings? How do emotions and feelings work, like happiness and anger and so on? It's an interesting question. It's not completely known, but in a sense, emotions seem to be sort of a global setting about the brain. Like a lot of what we do when we talk about things, when we think about very specific things, they're very specific, detailed aspects of what we're thinking about. We might and they involve very elaborate, probably very detailed patterns of activity in our brains, patterns of electrical activity in our brains. When we think about some math problem or something, we're probably dealing with some very elaborate pattern of electrical firings in our brains that represent those kinds of thoughts and so on. When we're just like, I'm happy, I'm sad, whatever else, that seems to be a much more global thing in our brains. And I think the general belief is that those more global things are associated with sort of a whole wash of chemicals, neurotransmitters typically, through our brains, rather than something which is a more detailed pattern of electrical activity in some particular region of our brains. And I think that that's why kind of various kinds of drugs and things can have an effect on sort of emotional state, probably more so than you don't take a drug that specifically lets you learn how to do integrals in calculus or something. So they tend to these things that have sort of a global chemical effect on our brains. Now, to what extent, how does that actually work? How does it translate from a neurotransmitter that makes it more likely for certain nerves to neurons to fire or whatever else? How does that translate into a feeling of I'm happy? I don't think we really know that. The one thing that we do know, it's something that's been realized, for example, Charles Darwin noticed this, is that the expression of emotions between sort of humans and animals is somewhat similar. I mean, even the kind of the mouth, the smile, the growl, or whatever else, similar between humans and dogs or whatever. And so it seems like there's this kind of global mechanism, this sort of emotional communication, emotional state that exists not just in humans, but also across a wide range of animals, at least the mammals. And I think that that's, for example, if there was a thing a long time ago, I'm really surprised that there hasn't been more work done on this, of sort of the human-dog communication process. And, what can your dog be saying? Woof, woof, whatever else. There's an extent to which one can, rather than the dog saying, I just figured out the solution to this equation, which is very unlikely probably for a dog to be saying, it's like, I'm a happy dog, I'm an unhappy dog, I'm a hungry dog, perhaps, whatever else. And these things are things where there's sort of more global features of the state of the brain of the dog that come out in sort of vocalizations that one can more readily translate into something. And by the way, the concept of I'm happy, I'm sad, whatever else, seems to even transcend different species. And there's at least a certain extent to which that's something where it's probably the same neurotransmitter that is representing these kinds of things. Now, when we talk about emotional states, it's sort of interesting to ask a question. Can we sort of define a space of emotional states? Just like we can say, I don't know, something that's often done these days is with computers is so-called sentiment analysis. So you read a piece of text. It's a review of some product somewhere. And the question is this a positive review or is it a negative review? What is the sentiment of this review? Does the person say, this product is just fantastic, this product is a piece of garbage? These are, you can rate those on different sort of sentiment scales. And so there's a question, just like you can rate sort of the sentiment, it's kind of going from happy with the product to sad with the product or something. It's kind of defining an emotional state with respect to, let's say, that product. Can you do the same kind of thing? Can you define a kind of a space of from happy to sad, from angry to content, from this to that? And there are a variety of things over the last probably 100 years, and it was particularly popular, probably in the early part of the 20th century, to try and make up these emotion spaces, which were kind of a representation of these different sort of things where you choose, it's in one direction or it's another direction. Where are you in this sort of emotion space? And I think it's quite possible that the people found these sort of emotion spaces that have maybe 3, 4, 5 parameters, from alert to completely not paying attention, to this, to that, to the other. And I think there's at least a chance that those different parameters correspond very directly to levels of different neurotransmitters in our brains, and that really is a pretty direct way to understand, how alert are we, how this are we, how that are we. So, but I think it's an interesting thing to the extent to which, for example, when we have verbal communication, we got words, you say certain words, they have certain implied kind of emotional content. You look at facial expressions, they have a certain implied emotional content. Same with voice, the quality of voice timbre, things like that, have a certain implied emotional content. To what extent can you roll back and say, what is the underlying emotional thing that's going on in the brain? And to what extent do you take the words that are said and then have sort of this overlay of emotional state? Some human languages have a much more elaborately tonal and things than, for example, English is. And I think that there's certain extra levels of communication that one can expect, which communicate various kinds of things, sometimes content there, but also potentially emotional state. So that's but I mean, if you ask the question, the question was asking, why do people have emotions and feelings? It's always a difficult question in biology, why? Because, the one thing we know about biology is if an organism is a particular species of organism dies out, then we're not even talking about that species. So the important thing in biology is for a species to keep going. And the fundamental way that any modern species keeps going is sort of have more children, so to speak. I say modern because back in very early species didn't really have this notion of cycles of life and death and generations and so on. But for the last couple of billion years, probably maybe at least billion years, it's been sort of a story of have more offspring to be a successful species, so to speak. So often in biology, there's sort of these questions about how does some attribute of a biological system have an effect on improving your propensity, your likelihood of having offspring, on improving your fitness to have offspring, and so on. And it's sort of it's often interesting to go back and see, can you figure out what aspect of this thing that is a feature of biological organisms helps in, why does it help in having more offspring? Now, sometimes people get very confused because they look for that, but it turns out that's not what's going on. It turns out that the feature of the biological organism is just a consequence of how the organism grows, or some other piece of the development of the organism that has nothing to do with fitness. It really is just a sort of side effect of the way that the organism has to sort of grow has to grow out the horn that it's growing or something. It has to have this feature because that's sort of just the way horns grow, so to speak. So in terms of emotions and so on, interesting question. I don't immediately see. I'm not sure I can immediately describe. I mean, there's probably things in. It probably depends a bit on how the organism works with respect to. Is it a very herd-like organism, or is it a loner type organism? There are different things, hunt in packs, or they're lone wolves or whatever. I think those wolves tend to be in packs, which is why you identify sort of the lone wolf idea. But there are other kinds of organisms that, like cats, for example, that tend to be very one creature for itself, so to speak, rather than we're just going to have a big pack that we're existing in. I suspect that emotions have a role in the way that kind of things work in packs. I suspect also they have a role in the way that one very direct one will be for mammals, at least, will be sort of taking care of the young, so to speak. And that's such a cute little creature, let's take care of it, so to speak. That's sort of an important thing for the survival of the species. If you expect to have, organisms which sort of get born where sort of the baby phase isn't very sophisticated and the baby phase can't fend for itself, then you have to make sure that the parents sort of take care of the offspring until it gets to the point where it can leave the nest, so to speak, and go off and fend for itself. So anyway, a few thoughts about origins of emotions. I think an interesting question I don't know the answer to is how low on the chain of life you see emotional responses. Certainly see them in mammals. I don't know if you see them. I'm trying to think. Do you see them in birds? Well, you see birds chirping, chirping, chirping happily. Whether one can identify clear emotional responses there, I do not know. I mean, I've never really heard of anybody talking about a sad fish, so to speak. That doesn't seem to be a thing. There are sort of other attributes of organisms that are sort of global brain attributes, like sleeping, for example, which does happen in fish. But I don't know of emotional states of things like fish. So that's a good question. I'm not sure. There's a question here I noticed just, wow, all kinds of comments here. There's a question from William. In the space of all possible mental states, what is the ratio of positive versus negative states? Is this a relative quantity? Does it obey transformations? Interesting question. I mean, look, my personal observation about us humans is that many of us get sort of thrown a random thing, which is our sort of average mental state. I'm happy about it, so to speak. I'm generally a pretty happy mental state kind of person. And yet, even when really good things happen, it's okay, it's great, but it doesn't really make my mental state go much up. When bad things happen, it's bad, but it doesn't make my mental state go much down. And I know plenty of people, just as a matter of sort of human experience, where it's like they're sort of always happy, they're always sad, and they can be always sad even if fantastically good things happen to them. They're still somehow always sad, and that's I think it's one just one gets used to a certain mental state, and maybe I don't know whether maybe I've just chosen to call the mental state that I have a sort of a generally happy mental state, and maybe to the outside it would be like, oh, that person is just grinding tenaciously on the work they're doing and they don't seem happy at all. But to me internally, at least, it seems like it's like, okay, great, things are good, so to speak. So I think it's a little bit in the maybe in the eye of the beholder, what counts as positive versus negative. I think, when people do experiments on rats and so on, they often try to assign mental states to rats. Oh, this rat in this particular setting is, it's a depressed rat. Because why is it a depressed rat? It kind of hangs out in the corner of the maze and it refuses to do anything. Or it's a very, a very excited rat. It's going to explore the maze in a very excited way. I mean, I would say that there probably are measurements that can be made for humans that of sort of mental states. And I didn't mention this earlier, but as we know more sort of personal analytics data about ourselves, there are things that one can certainly measure. I mean, one can certainly measure not only the sentiment of, oh, I'm typing wonderful email, talking about how terrific the world is, or another thing is, you look at your sort of social network and you're asking, are you connecting out to lots of people? Now that's to some extent am I an extrovert, am I an introvert? Or am I like, I have been connected out to a lot of people, but I'm really retracting and not talking to anybody. And that's kind of probably a sign that your sort of mental state is going more in the negative direction. But, and I do tend to think that in sort of assessing mental states and so on, it's kind of like if you're trying to, help somebody understand their psychological state and so on, it's at least the way of the future is, okay, can you give me the last year of social media communication? Let's go analyze what happened here. And, what can you tell from that about what's going on? But I don't think, somebody else commented here that if people didn't have emotions, then nothing would ever get done. That's interesting. That may very well be true. If I think there's a certain tendency, and it's identified not just in humans, of, are you interested in going out and exploring and going and, and finding new things? Or are you more like, just, I want to nest and be be comfortable, so to speak? And I think those are, that's one of these sort of set points for different people and different times of life and so on, that that one notices. But I think, and so sometimes there are, it's always an interesting question. What is it that, the motivation that people have to do things is often very complicated to understand. It often has to do with their own history, their interactions with other people and so on. And I suppose it's the case that in general terms, if nobody felt anything, then quite possibly that they wouldn't feel motivation either. And so as Kat was saying here, then nothing would ever get done. The question here from Dan: do you think the set of emotions is finite? That's a very interesting question. Is it possible for evolution to bring a new kind of emotion, or can we artificially create a new kind of emotion? I think that's a very interesting question. I think that insofar as it's true that emotions are associated with actual neurotransmitters in our actual brains, we're probably stuck with what we have. You could ask the question, if you have some bizarre drug, it's probably not a great idea, because brains have been evolved for a long time, and throwing some other random thing in is probably a super bad idea. But you could say, can you develop something which would sort of affect our brains in a way that is very different from the way that our existing neurotransmitters do it, or whatever else? Or is there a sense in which, the thing that always strikes me, with respect to the human condition and things like human emotions and so on, you watch a play written by some ancient Greek playwright, and the things that are going on are at a human level so absolutely identical to the kinds of things that go on today. It's clear that over the span of those few thousand years and all those changes in technology and culture and so on, nothing has changed really in the core of the human condition. And I think there's a sort of an interesting question: what can change in sort of the core of the human condition, and in things like kind of the possibility for different emotions? Like, for example, let's imagine that we had a really close link between our brains and some digital device, some very close neural connection where some digital device was reading out lots of aspects of what we're thinking in our brains and feeding back, you should do this, you should do that. It's potentially a quite, it's a very difficult to parse out. Is this good? Is this bad? Is this absolutely disastrous? There's certainly settings in which that could be, and certainly science fiction has covered some of these, in which that notion of the sort of externally engineered kind of way of getting people to think things is absolutely disastrous. It's bad enough kind of trying to persuade people of things by education, telling them the world works this way, the world works this way, the world works this way. Doesn't matter what you think, you're being told the world works this way. But if that's something that is directly being inserted directly into your thought process in your brain, that's yet a different thing that has the potential for sort of bad ends to history, so to speak. But I think that there's sort of a question of, assume that you could sort of feed into the brain all sorts of things in response to external stimuli. Could you do that in a way that was very different from the way that happens right now, and that we would read as sort of a different emotion? Interesting question. I tend to think, so here's a way to think about that perhaps. In our sort of higher cognitive processes, the main way we express those is through language. People invent some new concept, the idea of a live stream or something, and that becomes a word in our language. Then we get to talk in terms of it. People get to, build sort of a stack of ideas about that, and so on. But as time goes on, language evolves, and we end up with different kinds of concepts, different levels of abstraction that we express in language. So far as I know, that has not happened with human emotions. So far as I know, and maybe I'm wrong, but so far as I know, unlike language, which is this thing that is progressively building over the course of civilization. Human emotions haven't worked that way. And perhaps it's no surprise that emotions are also things shared with other animals, and which don't have the same kind of ability to, or don't appear to have the same kind of ability to sort of build with language progressively through generations and sort of build up the civilization of the cats or something. So I think it is an interesting question whether there is a sort of language of emotions that can be more elaborate than. But I think perhaps the other point is, with language, we get to communicate one generation to the next. We get to communicate ideas. I'm not sure we do that really with emotions. I'm not sure that that's the same type of communication that can happen in that way. Anyway, these are interesting questions. Let's see, there's a question here. There's a question here from Jake. Given that our brains are most likely the source of everything, yeah, I think that's a good assumption. Is there a finite set of combinations of matter in the brain? Could there be a finite set of all possible thoughts? Yeah, it's finite, but it's really, really big. And the thing to understand is about sort of combinations of things. It's like, how many possible passwords can you have on your, let's say you've got a 10-letter password. How many possible passwords can you have? It's a really lot. It's probably, is it more than the number of atoms in the universe? 10 letters? Can't work that out instantly. Have to type it in to know that, but it'll be comparable at least. I think that the thing to understand is that when you have even a fairly small number of possible of items, each one of which can work differently, the total number of combinations is very big. It's just like with music, you're playing on a piano, maybe there are 88 notes altogether, but maybe there are, I don't know, 20, 25, 30 notes that you would commonly use. But the set of possible musical pieces is absolutely immense. And it's so immense that, in the history of the universe, if one had been playing these pieces, all the pieces, across the history of the universe, we wouldn't even be close to having exhausted all of them. So the thing to understand is when there are lots of independent things that get picked, the total set of possibilities is really huge. So when it comes to brains, we might have on the order of 100 billion neurons in our brains, maybe some number of trillions of connections between neurons. And each one of those connections might be in one of thousands of states. And then if you work out sort of what does that mean, what is the total? It's 1,000 to the trillion or something. That's an incredibly huge number. That's a number so big that certainly in the history of our universe, we're not even close to beginning to take a little bite out of all of those possibilities. So the fact that it is in principle finite is not a useful statement in terms of saying, oh, you could only think about these number of things. Now there's some organisms that have many, many fewer neurons in their brains. Like, for example, one organism studied a great deal is a little critter called the nematode, the C. elegans, and it has about, altogether, it has, let's see, 1,700 cells, I think, of which about a few hundred are in its nervous system. So it has a small number of neurons, and you can kind of see for all of its neurons, people know to some extent what does that neuron do. By the way, unlike us, when our brains form, neurons go to, the ones that are going to make our visual cortex go roughly to the back of our heads, the ones that are going to make different parts of our brain go roughly to different places, but we're not specifically wired in a particular way. If you're a C. elegans with only a few hundred neurons, then you're wired in a very specific way. Like, this particular neuron is connected to this particular tentacle and it does this particular thing. This particular neuron is connected to some, smell sensor, and if it detects this, then it does that. It's much more of a special purpose piece of hardware than our brains are. But you could ask a question. I mean, for a creature like that, how many brain states does it get into? That's a much more finite number, and that's probably an answerable thing. By the time you're at an ant, I think an ant has 50,000 neurons, if I remember right. By the time you're even at an ant, you're at a just absurdly huge number of possible combinations. And so the thoughts of the ant are already far greater than you can sort of expect to enumerate. Okay, let's see. Questions here. Well, there's a specific one from David. Did I ever meet Isaac Asimov and/or Arthur C. Clarke? Unfortunately, I never met either of those two. I knew Isaac Asimov lived in Boston, actually, and I certainly could have met him. Although by the time I was sort of out and about, and we had quite a lot of mutual acquaintances, he tended to very much be just like everybody is during this pandemic, somebody who just hung out at home and wrote books. He wasn't really an out and about kind of person. Arthur C. Clarke, I certainly exchanged letters with, and I never met him. I think we talked once, but he lived the last many years of his life in Sri Lanka, which is not a place that I've been to, so I didn't have a chance to meet him in person. But he was always a very, in my interactions with him, a very positive person. Let's see. All kinds of interesting questions here. Let's go back a little bit. Okay, here's a question from Alan. Water evaporates from the ocean and moves up. The water doesn't spread uniformly over the sky. Water vapor coalesces into discrete clouds. Why is that? How come the humidity inside a cloud is 100% and right next to it is practically zero? Oh, you're giving me interesting, difficult questions. Well, let's see how well I can do on that. The most relevant thing to say, okay, so first point is, when water evaporates into the atmosphere is not completely uniform. There are always air currents, wind. There's always convection where hot air is rising, cold air is falling, things like that. It's not completely uniform. So there will be some parts in which there's, the humid air is being pulled up higher and will then cool off more and coming down in some other place. There's a whole sort of dynamic process of how things are moving around. Now, water and the sort of interaction between water and air is pretty complicated. The properties of humid air are air. Okay, so air has certain properties associated with being it's a gas where, for example, if you heat air up, it expands. If you increase pressure, I mean, there's a formula, the so-called gas laws, that say for an ideal gas. So an ideal gas is a gas where basically there's a lot of space between molecules. And so in a first approximation, what's happening in, for example, the air, which is pretty close to an ideal gas, is the molecules are just, all they're doing is just hitting each other like hard billiard balls or something. They don't have a force of attraction between them that's important. All that's important is when they run into each other, they bounce off. And in a gas that has that form, there's a definite relationship between pressure, volume, and temperature. So temperature of a gas is basically the speed with which all these molecules are bouncing around. The pressure of the gas is kind of, if you have a bunch of these molecules in a box, how many of them are going to hit the wall and bounce off? Because pressure comes from a molecule bouncing off the wall of the thing that you're using to measure the pressure. Because when it bounces off, it's like anything where it hits the wall, it pushes the wall a bit as it bounces off. And that force associated with it pushing the wall, that's what leads to pressure. And then volume is just how big is the box that you're putting the gas into. So the sort of the big law of the big gas law discovered in the 1600s is PV equals a constant times T. Pressure times volume equals a constant times absolute temperature. So that, and that's what's true for an ideal gas, a gas where all that happens is atoms run into each other. Now, there are effects that don't happen in an ideal gas. For instance, when in a real gas, molecules, it's not quite as easy to pull molecules apart as you might think. The molecules have a certain force of attraction between them and so on, and that leads to important effects. And in the end, what that leads to is the possibility that the gas, when you cool it down enough, will turn into a liquid. Because if it wasn't for the fact that there were forces pulling these molecules together, the thing wouldn't condense into a liquid. Okay, so what happens in the case of, so that's sort of the ideal gas law. When you mix air with water vapor, the whole thing becomes vastly more complicated. And there's this thing called the phase diagram, which is a diagram that shows usually volume versus temperature. It's the most common phase diagram. Is that right? Yes. Yeah, this is about to get quite complicated. Okay, so among the complicated issues is, okay, so for water, so water exists as a liquid. Water also exists as a gas, steam. Usually we're used to the idea that as you increase the temperature of water, you boil your water, the water goes from being a liquid to being a gas. Okay, all straightforward. Okay, now it turns out that as you change the temperature of, as you change the pressure of water, there comes a point in this phase diagram that's the so-called critical point of water. And at the critical point, the line that sort of separates liquid from gas is no longer distinct. So you get into this state where there's sort of you can't really tell if it's a liquid or a gas. And at that point, there are all kinds of interesting effects that happen. So one thing that happens is that effectively you get sort of droplets of all sizes. And that's kind of why you can't tell if it's a liquid or a gas. It's kind of got liquid droplets and they're of all sizes, but also they're kind of all floating around freely, and so it's a gas. And there are all kinds of features of water at the critical point. One thing is that there are features on all scales, and it's a thing very much liked by theoretical physicists, because there's very elegant mathematical theory of scale invariance associated with it. You change the scale at which you're looking at it, you see droplets of different sizes on any scale that you look at it. That's kind of what's happening in clouds. And one of the reasons clouds are white is because of this phenomenon of that it's water at the critical point. Now, why am I yakking on about this? The reason is the formation of clouds is associated with, it's a sort of complicated relationship between the properties of water vapor interacting with air and what that means as the cloud forms, how that affects things like the temperature, pressure, volume of the air. And there's quite a bit that is not understood about the formation of clouds. I should explain this. And there are different kinds of clouds. So for example, a typical thing that happens in a cumulus cloud, the fluffy clouds that happen at like 10,000 feet or something, fairly low, or less than that, fairly low clouds. The typical thing that's happening there is that there is convection. So that means that there's hot air rising, cold air falling, and that is bringing what does it do? It brings the water vapor up to the point where it has cooled to the critical point. And I think that's where the cloud forms. And the base of the cloud is where you reach the critical point for water, I think. And anyway, so that cumulus clouds are associated with this sort of updraft and downdraft, and cirrus clouds, which happen at much higher altitudes, are a somewhat different phenomenon. Now there are so many complicated things here, and much that I don't know about. One of the questions is, what causes a cloud to form in a particular place? And so there's a whole discussion about, can you seed clouds? Let's say you want it to rain. You don't want it to rain. you're putting on a giant sports event, you're putting on the Olympics or something. Do you want to make sure it doesn't rain over the Olympics? Can you fix the atmosphere so that that doesn't happen? So there's been a long discussion about what you can do along those lines. And there's a long discussion about what causes a cloud or droplets in a cloud to form in a particular place. And there's a question of whether the droplets require kind of a seed to form, whether there's a grain of dust, whether there might be something that is a leftover thing from a lightning storm or something, or leftover ion or something like this, that that is the sort of the seed that allows a droplet to form in a particular place. And so one of the things that has been experimented with for more than 50 years now is this thing called cloud seeding, where typically you have a plane fly over and it drops out a bunch of, I think, silver iodide, I think, is one of the substances that's used. Is that right? Doesn't sound right, actually. Anyway, there's something that you use as a kind of seeding agent, where you've got little tiny grains of this, and the idea is that those form sort of nucleation centers for water drops that will then turn into a cloud. Now, once you have a cloud, there's a question of, is it going to rain? And to what extent does the drops of water get kind of kept aloft by, for example, updrafts of air and things like this, and what makes them sort of fall out of the sky? And what tends to happen is in a cloud, the water drops, first of all, they sort of gain in size by just condensation of water. So you've got a water drop, and if the cloud is, I guess, cold enough, you will get there'll just be more water vapor that goes from steam to liquid water to make a bigger drop. And at some point, the drop gets heavy enough that it can no longer get sort of held up by the updraft of air that's sort of keeping the cloud in place. And so eventually the water drop will fall out of the cloud, and then it falls as rain. But the thing that tends to happen is that there comes a critical size. I have a vague recollection, it's 18 microns, but I might be wrong, where the drops are big enough that they no longer grow, that they start running into each other, and they start accumulating to the point. So the eventual way that raindrops get bigger is because the raindrops run into each other, and lots of small drops turn into a big drop. So first of all, they form by condensation, just water vapor forming onto a single drop, and then the drops start running into each other, and eventually they get big enough and they fall out of the cloud and they fall as rain. That's and I know it certainly used to be the case. I have not checked into this in probably a couple of decades now. It used to be the case that it was very mysterious how you could go from kind of a cloudless sky to having a cloud that was actually raining in a matter of 15 minutes. That it wasn't very well understood how you get sort of drops that are big enough to form in the cloud in order for that to happen. So a little bit complicated, and lots of things I actually don't know about how that all works. It's always a big issue. The modeling of clouds is a complicated issue. When people try to make climate models, for example, clouds are one of the most uncertain things of how will clouds be formed, how many clouds are there going to be, what effect will the clouds have. Clouds are difficult. It's partly because of this whole interaction between the properties of air and the properties of water vapor and so on. But clouds are, if you run into people who say, I know how to model the climate, I'm going to be able to figure out everything about the future of climate on the Earth. You say, it's a good question to ask to what extent you manage to capture what happens with clouds, because clouds are pretty important. I mean, clouds are not only do they affect the amount of, for example, they reflect sunlight back, they affect the amount of sunlight that reaches the ground, they affect a lot of things about the circulation of air and so on, and they're complicated and not completely well understood. All right, let's see. There's a question here. Oh boy, there's a question here about the movie The Matrix. The problem with these movies is I see them once, I think they're cool, I have a decent memory, but I don't watch them again. So my memory of these things probably decays over time. I think that The Matrix it's sort of, I found it kind of, you can ask the question, if you're going to try and explain a bunch of philosophical issues, what's the right packaging to explain those issues? It was a pretty cool piece of packaging to explain a bunch of those issues. I mean, I kind of wonder in the later Matrix movies, I did wonder, and I have never really tried to find this out, whether the people who created the Matrix knew about a bunch of science that I've done, because there were definitely aspects of particularly the end of the whole thing about the source and I forget, sort of the construction of the universe, that seemed awfully reminiscent of things that I was figuring out in the 1980s and so on. But I don't know whether there was a causal connection between these things. I think that as kind of a metaphor, well, I think this whole question of sort of the relationship between sort of the pure humans and us as humans, and kind of the digital world, and I mean, there's this whole issue of which I think the Matrix to some extent explores, and I must admit my memory of exactly how it explored it is a little bit fuzzy, but these questions, which means like there's no need for a spoiler alert, because I don't remember enough of the story to be able to spoil anything, but this whole question about to what extent sort of humans do what they do with free will, to what extent we are kind of determined by the laws of physics, for example, to do what we do, to what extent that is equivalent to being determined by sort of computational laws. Now, in the work that I've done on sort of the relationship between physics and computation, and particularly recently understanding a lot about the fundamental theory of physics, we're coming to realize that, yes, our universe is just sort of a giant computation that's happening. All the progress of time in our universe is just the execution of a big computation. And we are part of that computation, and all the things we do are represented by part of that computation. Now, the thing that you might say, well, that's really a very depressing outcome, because it's like, well, all we're doing is just being part of some big, completely determined computation. But the thing that kind of gets you out of that box is this phenomenon I call computational irreducibility, which is the fact that even though you know the rules by which the thing operates, if you want to know what's going to happen after a billion steps of running those rules, there's no way to know that other than by basically running those billion steps. So in other words, we don't get to jump ahead and say, so the outcome of our lives is X. We still have to sort of live our lives to understand that outcome, or to know that outcome. And I think the Matrix actually did have some kind of computational irreducibility thinking in it, which I'm kind of guessing would have come from things I wrote in the 1980s, but who knows? It's computational irreducibility, the idea of computational irreducibility, the idea that you can kind of know the rules for something and not be able to sort of predict more efficiently than the thing itself what's going to happen. That is an idea that in a sense is really originated with things like Gödel's theorem in mathematics in 1931, things like the halting problem in Turing machines and theory of computation with Alan Turing in 1936. But it was not really understood as a thing that was relevant to physics until stuff I was doing in the 1980s and so on. It was always thought to be something that was, well, it's relevant to these computational systems, mathematical systems, but that's different from what happens in the real world and in the physical world and so on. So I think that's some, but computational irreducibility is a very, if there is one thing that comes out of a lot of the sort of fundamental thinking that, for example, I've done about how computation works, it's this phenomenon of computational irreducibility. It is the ultimate limiter on science. That is, when we do science, we think we're going to find out the fundamental rules of a thing in the universe. And then once we found out the fundamental rules, we might think, then we're done. Once we know the rules for water vapor and this and that and the other, then we can compute what's going to happen to the climate on the Earth or something. But it isn't true. And it's in fact one of the sort of fallacies of modern science. The last probably 300 to 500 years, people have kind of gotten this idea. What science is all about is kind of drilling down and finding these fundamental rules, and then we're done. Then we can figure out everything. Science can give us all the answers. What computational reducibility shows us is that that's not the case. From within science itself, there are fundamental limitations. The actual systems in science are ones where there is no way to predict what they're going to do other than by essentially running them and seeing what happens. And that's a consequence of this thing I call the principle of computational equivalence. But it's also that phenomenon is this phenomenon of computational irreducibility. So what is to me interesting in terms of the sort of flow of history of science is, what we learned from Copernicus, Galileo, Newton, and so on was really this idea that we could have these rules in science, these theories of science, which would let us from this theory predict all this stuff. And we just kind of have made this implicit assumption that means we can predict everything. And it isn't true. Science from within itself has this built-in limitation that prevents certain things from being predictable and requires that you basically just run them and see what happens. And I think that's an important thing to understand. It's important not only in understanding science, but also in understanding things about sort of what it means for artificial intelligence and what it means for the predictability of that and what it means for whether we can say, can we tell that the AIs are always going to be good to us or something? Well, no, because of computational irreducibility, basically. Anyway, long story. There's a question here about my thoughts on recent superconductor breakthrough. Yes, I noticed that. I have not studied it. I don't know. Let me explain what superconductors are just for people's interest. So when you have a wire, electrical wire, you try and push electricity through it. You have a voltage. A voltage is kind of the force that's pushing electrons through the wire. In a typical wire, like a copper wire or something, the electrons go through pretty well, but there's still some resistance to the electrons going through. That leads to resistivity in the wire. That means that even though you're pushing with a certain voltage to get these electrons to go through the wire, the current, the rate at which electrons go through the wire is limited. There's sort of pushback from the structure of the crystal lattice. And what's happening is the electrons are trying to go through this arrangement of copper atoms, and some of the electrons are roughly sort of floating between copper atoms and just being able to get through, but it doesn't quite work precisely like that. There is some resistance that exists to the flow of electrons through the copper wire. So a thing that was discovered in the first decade of the 20th century was a phenomenon called superconductivity. If you cool certain wires down far enough, I think lead and niobium were early ones that were discovered. If you cool the wires down to a low enough temperature, the resistance to the electrons goes down and down, 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 down. And then suddenly, at a critical temperature, the resistance to pushing electrons through the wire goes to zero. Not just small, but actually zero. Electrons, you put a tiniest voltage you can imagine on the wire, and electrons will just be pushed through it as fast as you want, or as many as you want. So that's the phenomenon of superconductivity. And once you have a superconducting wire, you can get a current to flow through that superconducting wire. You can get lots of current to flow through, and there's no resistance. Why is resistance important? So let's say you're trying to you've got an electric power station, and it's generating lots of electricity, and you want to transfer that electricity to some place that's 1,000 miles away. Well, you put it through a wire, but there's a resistance to getting that electricity through the wire, and that resistance to what actually happens is that the sort of the force you try and push things through with doesn't succeed in getting all the electricity through. Instead, some of that force is just turning into heat. It's not successfully pushing electrons through, it's just turning into heat. And so when you see electrical wires, turns out the higher the voltage that you're using, the less, compared to the amount of current you're getting through, the less heat you produce. It's still the case that you can't get rid of the heat that you're producing unless the wire is superconducting. If the wire is superconducting, then the resistance to pushing the electrons through is zero. No heat is generated by getting the electrons to go through the wire. Now, in there's a little bit of a catch, which is that superconductors typically, if you try and put too much current through them, the current produces a magnetic field, and the magnetic field actually breaks down the superconductivity. So superconductors usually have both a critical temperature. If you heat them up too much, they stop being superconductors, and a critical magnetic field. So basically, if you put too much current through the superconductor, it stops being a superconductor anymore. Okay, the question from Flying here. If the resistance goes to 0, would the electron start accelerating without bound? It doesn't actually accelerate without bound. I'm a little bit cheating in describing the how this works. The fuller story, oh boy, can I get to this fuller story? The fuller story has to do with the so-called conduction bands of, it's a story of quantum mechanics. And essentially, it isn't really right to think about individual electrons being pushed through the wire. What's really true is that there's this kind of delocalized electron field that exists in the wire. And when you're putting a voltage, you're sort of distorting that electron field. And so it's not really a question of just saying, individual electron go faster, faster, faster. Electrons go through wires at a fraction, maybe a tenth of the speed of light, usually. In some sense of measuring that, you can sort of send a signal through a wire at a certain speed. Now, anyway, about superconductors. So, for quite a long time, nobody understood how you could get down to sort of 0 resistivity for electrons going through a wire. What was realized is that actually the phenomenon of superconductivity is basically the same phenomenon as the phenomenon that causes lasers to work. And the way lasers work is essentially you've got a bunch of photons and you arrange it so that kind of all the photons in the laser want to do the same thing. They all kind of want to be exactly lined up, exactly in phase, so that their light waves are all lined up, and they want to be going in exactly the same direction, making a laser beam. And that phenomenon of things wanting to sort of all be in the same state is a phenomenon of quantum mechanics associated with so-called bosons, certain particles, and this gets a little complicated, but particles that have integer spin, of which photons are an example, they have spin 1, like to get in the same state. If you put lots of photons together, they all want to do the same thing. Electrons, which have spin 1/2, work quite differently. If you try and push lots of electrons into the same state, they exclude each other. There's this thing called the exclusion principle, and that's actually why matter is stable, is because of that exclusion principle. Because if there weren't electrons and other spin 1/2 particles and so on, matter would just collapse. It's the fact that there's this sort of exclusion of things that prevents these electrons from all sort of occupying the same space and so on that causes matter to be stable. But anyway, so electricity is made of electrons. So there's a question of, can you get something like the laser case, where in the laser case, these photons are all sort of ganging up together. And so they kind of have, if there was a question of resistance and it doesn't work quite the same way for light, it would be like they're all in it together and they're all able to sort of push through together and overcome that sort of resistance. I think that the question of okay, how does that work for electrons, which like to exclude things, like to not be in the same state, was discovered in the 1950s or 60s, I think. What actually happens in superconductors is the formation of these things called Cooper pairs, which are places where pairs of electrons have paired up. And so the electron has spin 1/2, but these pairs have, for example, spin 0, because it's like 1/2 minus 1/2 gives you 0. And it's these pairs of electrons that allow you to get superconductivity. Now, there's a question of, okay, can we make a superconductor? The big question is, can we make a superconductor that works at room temperature? Most superconductors work only a few degrees above absolute 0 at temperatures of liquid helium and things like this. So they're very, they only work in very, very cold temperatures. Can we get a superconductor that will work at something like room temperature, so that we could use it in practical kinds of things that we're doing in sort of typical everyday settings. And that's been a big adventure to try and find high temperature superconductors. There was about 30 years ago, people found a set of materials that have very, very exotic materials with elements like lanthanum in them and so on, a whole sort of weird materials that are high temperature superconductors. But by high temperature, it means maybe 100 degrees above absolute zero, not reaching kind of room temperature, which is 300 degrees above absolute zero. So the thing that, so there's been this kind of big hunt on for, can one find a material that will make a high temperature superconductor? The theory of how even the high temperature, in quotes, high temperature superconductors that exist today work is really quite incomplete. So there's this question of, is there a way to find a material which, by some weird feature of the way that it interacts with electrons and the way that this and that happens, manages to make a superconductor at room temperature? And there's been some recent progress, which I really have not studied in the last couple of weeks on this. This is a challenge. If it is successful, it will lead to all kinds of cool things. I mean, the magnets that exist today, back in the day, most people just had iron magnets. But in the last probably 20, 30 years, so-called rare earth magnets made with elements like gadolinium and so on have become pretty common. And rare earth magnets are much stronger than ordinary, usually the magnetic elements are iron, cobalt, nickel. But there are other elements that are sort of below them on the periodic table, like gadolinium. I think samarium maybe is another one, but gadolinium is the most common one that's used for this, that have kind of much stronger magnetism. And so a lot of magnets that you'll find in a lot of modern sort of consumer electronics devices are rare earth magnets, gadolinium magnets, and things like that. If we had superconductors at room temperature, we would have all kinds of interesting, I should say that as soon as you have a superconductor, you can kind of make this loop of wire. And when you have a loop of wire with a current going around it, that makes a magnetic field. So you can use this to make magnets. You can use it to transmit electricity easily. You can use it for all kinds of purposes. Once you have a superconductor and you have a current going around a superconductor, it will go around for months at a time. It really doesn't, there really is no resistance to motion. All right, we should wrap up quite soon here. DVL is saying it's their birthday. Well, happy birthday, devil or angel. That's an interesting question. All right, I'm going to do maybe two more here. It's a question from Cambridge. Why doesn't every single thought episode last forever? Why does thought disappear after it arises? Why does our memory, for example, decay? When we think about something, why are we not why is that not sort of permanently etched on our brains, so to speak? Why does it decay away? I mean, we don't know completely how. So in a first approximation, our brains are working with electrical impulses in our neurons. And once an electrical signal, when a neuron has transmitted an electrical signal to another neuron, then it's gone, so to speak. That electrical signal is then transmitted on to the next neuron and it's disappeared. But the question is there a memory of what that signal was? And the answer is, well, probably not that we can access.